Video for investigation 12A, which is hurricanes. So we are on our last set of videos for the session. So this first of our last two videos about hurricanes is a general video in terms of it handling just kind of the general characteristics and traits of hurricanes and tropical cyclones. And then from here, what we're going to do in investigation 12B is move on to a case study of Hurricane Ian, which hit Florida and then eventually the Carolina coast in 2022. So let's get started on our PowerPoint and let's finish off these videos, shall we? And let's get started. Here we go. All right, so here we are at hurricanes. And what I want to do is I want to begin with figure 12A1, which is just a schematic, kind of a side view of what a hurricane appears to be. So first of all, I just want to begin in the middle of the figure where we have our low pressure system. This is the center of the hurricane, and you'll notice that the skies are clear here. So this is meant to be the eye of the storm. The eye is surrounded circularly by something called the eye wall. And the eye wall is basically a ring of extremely intense thunderstorm activity. And this is where we actually find our strongest winds in the hurricane. And then what you'll see outside the eye wall is that you'll get an area that is relatively calm, and then we'll have another band of intense thunderstorm activity that's a little less intense than the eye wall. And in fact, you'll see with a well-developed hurricane that you'll have multiple bands extending outward from the eye and the eye wall. Now, we have a couple of numbers on this figure, so I want to go through them one at a time, just to show you the movement of air, generally speaking, in a hurricane. So first of all, we have intense upward motion, intense vertical ascent in the eye wall itself. So you have really rapidly rising air. As this air rises, it expands and it cools, and you get a tremendous amount of condensation, thus the cause of an extremely heavy rainfall, and you have a tremendous amount of latent heat that's released. And in fact, it's this latent heat release that actually powers the hurricane along. And without this latent heat release, without the storm being over very warm water to provide the vapor for this latent heat release, these tropical cyclones simply would not exist. Outside of the eye wall, this air has to go down somewhere, and so you'll see with circle 3, you'll see downward flowing air outside of the eye wall. In fact, if we actually were to take a look at this at a more granular level, and we'll see this in our next slide, you get upward motion in each one of these rain bands extending outward from the eye wall. And it's not actually shown in these rain bands on the side here, but in fact, you've got upward motion in each of these bands and downward motion between them as well. And so you get these areas with a hurricane of extremely intense rainfall, then you'll get a break, then you'll get more intense rainfall, and then a break, and so on. And then finally, as with all surface low pressure systems, air swirls in towards the center of the low in a counterclockwise manner. So you get this counterclockwise and inward directed flow that actually follows the swirls of these rain bands in. And unfortunately, we don't have any really good satellite imagery with our two investigations, 12A and 12B, but you can find lots of great satellite images of well-developed Category 4 and Category 5 storms online. And for example, I would very strongly recommend that you get online and just take a look at some of the satellite imagery that was taken when Hurricane Katrina was over the Gulf of Mexico in 2005. It was an incredibly intense storm, almost a picture-perfect storm in terms of symmetry and rain banding. So, I mean, obviously it was a terrible storm in terms of destructiveness, but in terms of its formation, it was near perfect. Okay, this is figure 12A2. This is another schematic of a hurricane, and I'm going to put the numbers in again, 1, 2, 3, and 4 that we had in slide 1. But just to show you, here is a more three-dimensional view of the storm. Here is our eye wall and just basically outside of the eye. And then you can see just slicing through each of these rain bands as you move outward from the eye wall, and the height and the intensity of each rain band as you move out from the center of the storm gets weaker and weaker. The tops of the clouds get a little bit lower each time. But what you can see is that you have upward motion in each one of these rain bands and then downward motion outside of each of these rain bands. I mean, what goes up must come down somewhere. And so you do get these intense bands of rain, and then you get these breaks in between where the air is sinking and compressing. You may never lose the cloudiness between the bands, but there will be breaks in the intensity of the rainfall. Now let me put these numbers back in again. So number one, and I put it right here, air rises in thunderstorms. And in fact, I just put one in with the eye wall, but in fact, you could put one in next to each one of these up arrows. And again, the magnitude of the up arrow gets a little bit smaller as you move out from the center of the hurricane, indicating that the intensity of the upward motion and the thunderstorms and the winds get a little bit less as you move further out with each of these rain bands. Then you get condensation and latent heat release. And again, I'm just showing this in the eye wall, but I could put a 2 in each one of these rain bands as we move out from the eye wall. And again, you get latent heat release wherever you get this upward motion and condensation. Then again, you get the air sinking, and I put the air sinking, first of all, just showing you the downward arrows in one of these rain bands extending out from the eye wall. But I also wanted to indicate that we get downward motion as well in the eye, and it's this compression and warming that causes drying of the air in the eye, which leads to this circle. But with really well-developed hurricanes, this circle, which actually may be cloud-free, and it's typically calm as well. So when you've got a Category 4 or Category 5 storm, an extremely intense storm, the more intense the storm, the more likely it is that you're going to get strong downward motion to form a clear eye. And before people understood hurricanes really well, people would get tricked when the eye went over them in really strong storms, thinking that the worst had passed. But in fact, you then had to deal with the backside of the storm, and you'd end up back in the eye wall again. And this ended up really causing a lot of fatalities in hurricanes before we understood how these things were structured better. And then finally, as always, the surface area swirls in towards the center. Now, this is basically showing the swirling as just a counterclockwise and parallel motion rather than swirling in towards the eye wall. But in fact, you're getting inward swirling towards each of these rain bands. It's just not showing really, really well here. Now, you can see this dense cirrus overcast extending outward from the eye wall. But as you get further and further away from the center of the storm, this cirrus overcast will actually thin out so you can actually see the individual rain bands on satellite imagery. Okay, this next slide shows tropical storm tracks between 2000 and 2023. And this is really a great image, by the way. It shows basically anything that was tropical in nature. And you can see this gray for extratropical storm. This basically is what we see after the hurricanes have made landfall and have taken on the characteristics of an extratropical cyclone. In better words, they've begun to ingest cold air and form fronts and cold and warm sectors. But when you're in the tropics, basically you start with a tropical depression. This is the weakest category of a tropical system. Tropical depressions then can strengthen into tropical storms. And then tropical storms will strengthen into hurricanes. And you go in terms of intensity of hurricane from category 1, 2, 3, 4, and 5. And you can see all this color coding. This tangle of spaghetti, basically showing all of these storms and their evolution from tropical depression all the way through hurricane, back to tropical depression, and then eventually to extratropical cyclone, and then dissipation. One of the things that I think is really important to note here is the basic flow in terms of the movement of these storms clockwise from the tropical Atlantic Ocean into the Atlantic or the Gulf of Mexico, and then curving back outward again towards the north and then the northeast. We have this semi-permanent area of high pressure in the Atlantic Ocean that I showed you in an earlier investigation when we were just basically talking about the general circulation of the Earth's atmosphere. And what we see is that tropical cyclone tracks tend to just basically move along the southern periphery and then eventually the western periphery of the subtropical high, the semi-permanent subtropical high over the Atlantic Ocean. Also, and this is kind of unfortunate that it's not shown, but this diagram does not actually have lines of longitude in it. And the reason that longitude is important for the United States is because 75 degrees west longitude is a really important longitude. And what we see is that for storms that actually make it west of 75 degrees west, these storms are much more likely to make landfall in the United States, either along the Gulf Coast or the east coast of the U.S. If the storm actually begins to curve back out to the north and then the northeast to the east of 75 degrees west, then these storms tend to miss the U.S. and just basically stay out to sea and miss us altogether. So 75 degrees west is kind of a benchmark longitude that meteorologists look at in terms of the movement of these storms. And so if you have a storm again that makes it to the west of 75 degrees west, the chances of that storm making landfall somewhere in the United States really increase dramatically. So again, I'm sorry that we don't have longitude lines on this map, but if you want to, you can actually just get a map online. You can see where 75 degrees west is located, and you can see obviously that a lot of these storms that make it west of 75 degrees west did actually ultimately make landfall somewhere in the US, either along the Gulf Coast or along the southeast coast. Okay, some more characteristics of tropical cyclones. This is the Saffir-Simpson hurricane wind scale. And this is a scale that was developed by two scientists that, interestingly enough, was published in 1971, which is the same year that Ted Fujita published his original Fujita scale for tornadoes. And like Fujita, the Saffir-Simpson scale has a scale from 1 to 5, which basically is an upscale. Each step is a little bit more intense of hurricane intensity. You can see the wind ranges for each of the categories in kilometers per hour, and for us here in the US, obviously, we're more used to miles per hour. And like the Fujita scale, Saffir and Simpson basically developed their scale to basically equate these wind ranges with certain types of damage produced by the wind. And so you can get online, and again, just looking on your own, you can see what they define to be minimal, moderate extension, extensive, extreme, and catastrophic. As with tornadoes, anything that is category 3 or higher, and EF3 or higher for tornadoes, is considered to be a major event. So EF3 and higher is a major tornado. Category 3 hurricane or higher is a major hurricane. So these are just the categories that we use when we're categorizing hurricane intensity. And I believe this may be, I'm not sure if this is the last slide, I think this may be the last slide of our investigation. And what this is meant to do is just basically to show you how extensive the flooding would be if a Category 5 hurricane made landfall anywhere along the Gulf Coast or the southeast coast in the US. And the way to basically interpret these colors is to basically equate the color with how high the water would be on land if a Category 5 storm made landfall anywhere along here. So these reds basically mean that the flooding would be 9 feet or higher. And then you go down from 9 to 6 to 3, and then no flooding even with the Category 3. Now what they're doing here is they're actually interpreting these floods to be with storm surge. Now storm surge is not something that we're going to talk about a tremendous amount in these two investigations. But what the storm surge is it's basically the tidal surge that comes in with the hurricane along the eye wall. This surge is caused by the winds as well as the extremely low pressures with these hurricanes. And so what you see on top of wave height is just an overall increase in sea level as the hurricane comes in. And with Category 5 storms, you can have storm surges upwards of 20 feet plus. So these are incredibly catastrophic events when you get a very high storm surge. And in fact, the greatest number of fatalities caused by hurricanes is caused by storm surge, not by rainfall, not by damage from winds, not by anything else. It's storm surge. Now, obviously, hurricanes pose multiple threats, and so there are a number of ways that people can actually be taken out of the equation by hurricanes, but the largest number of fatalities result from storm surge. So for some reason, I'm not quite sure why, we have two insets here that don't really relate to our case study that we're going to be doing in Investigation 12B, but we have one for basically focused on Houston and the other one for some odd reason on West Palm Beach. So what you can see is that the Gulf Coast is much flatter than the coastline along Florida. So if you take a look at West Palm, even with a Category 5 storm coming in anywhere along this part of the east coast of Florida, although there would be inundation, you're looking at inundation of 3 feet above and maybe less than 3 feet above. So around Hollywood, maybe you'll get some flooding of 3, maybe 6 feet along the immediate coast. But most of what you see is 3 feet or less along the east coast of Florida. So even though Florida, most people think of Florida as being really flat, it's not as flat on the Atlantic side as it is on the Gulf side. And what I really think is most important here, and that we don't have an inset for, is Louisiana. Take a look at how extensive the flooding would be in Louisiana if we had a Category 5 landfalling hurricane anywhere along the coast of Louisiana. All of this red indicates that the inundation would be 9 feet or higher with a Category 5 landfall. So Louisiana really is of all the states that we have to deal with hurricanes, it is the one that poses the greatest risk to human life and just everything. So we've already seen disaster in New Orleans in the past 20 years, but Louisiana in general really is problematic in terms of flooding from storm surge. Okay, that is everything I want to say about the general characteristics of hurricanes and Investigation 12A. If you have any questions whatsoever about the investigation, feel free to ask me questions, post it on the discussion board, or ask me live during my office hours in Zoom fall session, Wednesday evenings 7:30 to 8:30, or Sunday afternoons 2 to 3 p.m. But that's it for this particular investigation. I'm going to end the video now and post it on Canvas, and when it's ready for you to view, you'll see an announcement.